Hello again, welcome to the third lecture for week 8. We're continuing on with our look at fluids. We started by looking at density and pressure and then static fluids. And so today we're going to continue by looking at fluids in motion. So we'll jump over to the slideshow. So motion of fluids. Remembering fluids means gases or liquids, but as you'll see, we'll bring in this idea of ideal fluid flow and discuss what that means and what limits that places on what fluids we're actually considering. We're then going to look at flow speed using a concept called continuity. We're going to introduce Bernoulli's equation. And just as we did with Archimedes' principle, we're actually going to build up to Bernoulli's equation. So we're going to go through quite a few steps, consider quite a few different things. And then by the time we arrive at Bernoulli's equation, hopefully it'll all make sense. We won't need to then go and explain it all. And we will then use Bernoulli's equation to solve problems. So the idea of all of this is to be able to take this equation that we're going to uncover and solve simple physics problems. So firstly, why? Why do we care? Well, it's extremely important, not just for physicists or engineers even, but to a lot of different areas of scientific understanding and human application. So we've got just a couple of quick examples: geological processes. We've got rivers, glaciers, oceans. Those are all fluids. Understanding how fluids flow will help us understand those natural phenomena. We've also got biological processes, so fluid inside living things. As we all know, we've got blood pumping through our veins and arteries at any point in time, being pumped around by the heart, and understanding the difference in fluid pressures at different positions and how the speed and other factors affect the pressure can influence our understanding a great deal of how those systems work. And finally, what may be more applicable to engineers and physicists in general is designing things that involve fluid flow. So if we're setting up an experiment, or if an engineer is creating a system which will have some fluid in it, then understanding how the fluid is going to flow will help us design that setup. So before we get started, we need to introduce the ideal fluid model. You're all familiar with the concept of making assumptions in order to be able to do some calculations and actually have physics equations that explain what's going on to a reasonable degree. As physicists, we like these models that come out with these assumptions in them, but we do have to be aware of those assumptions and therefore when they might start to break down, when those assumptions aren't going to be true. For the ideal fluid model, we have 4 primary assumptions that you should all be aware of, and that way you can identify a system that doesn't have these 4 assumptions being close to true, and you can say, well, this isn't going to reflect the real scenario because we've got these assumptions that aren't being met. So firstly, the fluid is incompressible. So that is, it's more like a liquid than a gas. So liquids are often very close to incompressible. They're not always perfectly incompressible, but they are close to it. Gases, though, as we should all expect, are very compressible in a lot of cases. So usually the ideal fluid model that we're going to look at doesn't work very well for gases. It can, but it doesn't always. The second assumption, the fluid is non-viscous. So if you stir some water, the water flows very easily. If you have syrup or honey or something like that that's really thick and sticky, it sticks to itself, it's a lot harder to stir. That's what viscosity is. We'll talk more about that in a moment. We'll also talk more about laminar versus turbulence. We need it to be laminar, we need it to be steady, and the flow is irrotational. So a disc placed in the fluid will move along but not rotate. So imagine you've got a river of fluid flowing along, and you take a little polystyrene disc or something circular, you put it on the surface of the water, and you watch as it flows along. If that disc doesn't rotate, then your flow is irrotational. Right? This just means there's no rotation. But if your disc rotates, that means that the water under one side of it is going faster than the water under the other, and it'll cause that rotational effect. So if that's happening, then we can't use our ideal fluid model either. As I said, we'll talk a little bit more about a couple of those things just so you can hopefully understand. Viscosity is like friction for fluids. When you think about a pipe full of liquid and the fluid flowing through it, hopefully you just picture all of the fluid as one big lump all traveling through the pipe. That's what our ideal model is assuming. So that's the picture you want to have. In reality, of course, the fluid can't move past the inside of the pipe perfectly because it will rub up against it, just like an object sliding on a surface. A solid object will have friction, this fluid will have friction between it and the pipe, so it won't flow past perfectly smoothly. There will be a bit of slowing down at the edge because of that viscosity, which is like friction. And then the next little bit of fluid in, so that's the very edge, is barely moving at all because it's rubbing up against the pipe. The next bit isn't rubbing against the pipe, but it is rubbing against the fluid that's going really slow next to the pipe. So that will only be able to go a bit faster, and so on all the way to the center of the pipe where you'll get the fastest amount of fluid flow. But the point is, anywhere you go in the pipe, how fast the fluid is flowing depends on how far from the edge it is. All of that we don't really care about, right? Just need to explain it so that you can say, right, if that's happening, we can't use our ideal fluid model. Okay, and that's what viscosity is. So we need non-viscous fluids where we can ignore any of that friction, that fluid friction or viscosity, and just treat it as one big body of water that's all fluid that's just traveling straight through the pipe and not actually experiencing any friction or anything with the pipe. And the other thing that we wanted to define is laminar versus turbulent flow. So laminar flow just means streamlines, right? So you've all heard the term streamlined. The air or whatever might pass something, a streamlined car, it'll go over the car very easily. When the path of a particle is very predictable, when it'll follow a specific path or a streamline, that's laminar flow. And turbulent flow is just the opposite. It gets messy. The particle might just move around randomly in weird little circles and all sorts of things, and we can't really tell where it will end up. That's turbulent flow. An image like this is a very good way to visualize laminar versus turbulent. So to start with, at the origin of the smoke, so further down this image here, we've got laminar flow. Right? So if you choose a particle anywhere at the start of this flow, then you know where it's going to end up because it's laminar. All the particles just slide up all alongside each other, just nice and smoothly. We get smooth laminar flow. But once we get to here, you can see that it starts to get turbulent. So turbulent just means it's moving around in all sorts of directions. It's colliding with other particles and doing all sorts of things. And we have no idea where that particle is going to end up once it gets into the turbulent flow. So laminar versus turbulent is just sort of an idea of whether we can predict where the particle is going to go versus we don't really know because it could do lots of different things. Obviously, for our ideal fluid model, we want the one we can predict. That's the whole point of physics, is being able to predict these sorts of things. And as I mentioned, we use streamlines to visualize this. So on the right-hand side of this diagram, we've got some smoke trails being released in front of the car. This car is in a wind tunnel, so the air is flowing from right to left over the car. And we release a smoke trail, and we see that as it goes past the car, it does start to spread out a bit. The more it spreads out, the less confident we are in where that particle will end up. But we still know that one that starts in this first stream is still going to be in that stream at the end. You can see that the ones, the very bottom ones, start to get a bit blurry, start to get sort of fuzzy. That's just the streamlines starting to get into turbulence, right? It's starting to spread out and not be predictable as much anymore. But for the most part, you can see that we have these nice smooth streamlines, so we have laminar flow for most of it. And of course, laminar flow is what you want when you have a vehicle traveling through air, because if it's laminar, you're getting less resistance. So let's think about fluid flow. So we've got a pipe or some scenario, and we've got fluid going through it. How much fluid is going into the pipe versus out of the pipe? Hopefully, you can all picture the scenario like I've drawn here. This must be a very tiny pipe because it's only got a few molecules in it. But imagine each of these green dots is a molecule or a droplet. I've written droplet, but droplets don't stay as droplets. So you can imagine it as a molecule or an atom if you want. But if this pipe is full, we can't fit any more in there. So if we want to put one in, one has to come out the other end. However many we put into the left-hand side of this pipe, we must have the same number coming out the right-hand side of the pipe. Right? So that's just the idea of this, this continuity of fluid flow. However much is going in must be how much is coming out because it's full. Right? We can't pack any more in there. So if we want to put another one in, it pushes one out the other end. And that's the idea that we want to really get stuck into. So as I said, that's called continuity, and it's just the idea that the volume of fluid you put into a pipe has to be the same as the volume coming out. So if you've got 1 second and you pour 1 litre into one end of a pipe, then during that same second, 1 litre must have come out the other end of the pipe. It has to go somewhere, right? You can't condense that liquid. Remember we said that our ideal fluid model as incompressible liquids or incompressible fluids. So if we're not compressing it and we add 1 extra litre in, then that means that a litre must come out the other end as well. Otherwise, we'd have too much liquid in our volume, in our pipe. The result of that is that if the pipe changes dimensions, then the velocity must change, because we still need the same volume out. So you can imagine this area here. If you put in 1 litre of water, it'll move all the water along at some rate, but it might not need to go too far because this is quite a big area. Whereas at the other end, we still need a litre to come out, but now we've got a smaller area, so that water must go quicker through that smaller area in order to get that litre out. So let's think about that in detail. If we take that area and we choose a particle that happens to be right at the front of this area at the start of adding our liquid, adding our extra fluid that we're pumping into the pipe, then in some time t later, it's moved along this far. Right? So that particle has flowed along this far, and every particle has flowed along that far because we've said it's not viscous and it's laminar. So we know that all the particles are doing the same thing. Any particle that starts at this area of the surface, this slice of water, will have moved delta x along in that time. And that gives us a volume, because we've now got an area times the length, and we have a volume of liquid. So we have a volume of liquid, and that distance delta x is given by the velocity of the fluid at that point. So remember, all the velocity is flowing at the same velocity. All the fluid is flowing at the same velocity. So that means that delta x is actually v1 times t. I've got ones in here because this is the wide part of that pipe. So that means that the volume in some time t is equal to a1, the area, times v1, the velocity in that area, times the time that it's traveling for. Then for the narrow part, it's the exact same equations, right? Exactly the same reasoning, exactly the same equations, but now we've got the smaller area A2, we've got a different velocity V2, and the volume V2, big V2, must actually be the same as the volume big V1. That's from our reasoning just before, that if we're putting some amount of water in, we have to have the same amount of water out. I keep saying water because it's the easiest thing to visualize for a lot of people, but remember that this applies to any ideal fluid. Anything that matches our ideal fluid model, we can think about this with. So we've got the V1, big V1, volume 1 and volume 2 are the same, and that means that A1 times velocity 1 times time is equal to A2 times velocity 2 times time. And of course we can cancel out the times, and we get A1 V1 is equal to A2 V2, where the V is a velocity now. So we've got the area times the velocity in the wide part is equal to the area times the velocity in the narrow part. And that is the equation of continuity. That is the result that is demanded by our flow having to be continuous. If we put a litre in, a litre has to come out. However much we put in has to come out. So that's that simple concept results in this equation, the equation of continuity. So if the area of the pipe changes, then the velocity will have to change as well. Sometimes you'll see these equations with a density included in the terms. Right? We just had area and velocity. Sometimes you'll see a density in there. The idea of including density is that the mass going in has to be the same as the mass going out. Right? We've said volume in and volume out are the same. Technically, the mass going in has to be equal to the mass going out as well. And if you weren't going to keep the assumption that the fluid was incompressible, then that mass continuity would be a more useful equation, because that would be true whether or not the density was changing. But because we know the density is not changing, because we've said our fluid is incompressible, we can drop the density out of our equation. We don't have to even think about the mass, because if we've got a fixed volume, then that's the same as having a fixed mass when your density is not changing. So you may see that with density sometimes. Generally, you won't need to care about it, but being aware of that is still useful. So we've got an example. We've got water flowing through a pipe of x centimeters diameter. This transitions to a pipe of half x centimeters diameter. And the question is, how fast is the water traveling in the narrow diameter compared to its speed in the wider diameter? We haven't been given any actual values, but we've been asked to find the speed compared to its previous speed. So we're looking for some kind of ratio or fraction. We'll jump over to the document camera and we'll just have a play with this for a moment. So we've got a pipe this will look very much like the diagram we just had. We got a pipe, and then it narrows to one with a half x diameter. So this is x, and this is half x. Now it says half x, x and half x diameter. That means that we are thinking about the area is going to be A1 is equal to pi r squared, which equals to pi x over 2 squared, which is equal to a quarter pi x squared. The area 2, so that's area 1, that's area 2. Area 2, same reasoning, but now r is a quarter of x. We've got pi r squared is equal to pi times x over 4 squared, which is 1/16 pi x squared. So that means that we know that area 1 is 4 times as big as area 2. 1/4 versus 1/16. If you wanted to, you could actually write that as a quarter times a quarter pi x squared. And that way you can see that this term and this term are exactly the same. And so area 2 is a quarter of area 1. So we know that area 2 is a quarter of area 1. And the question is, how fast is the water traveling here? We want to know the velocities. So if we set this to be V1, doesn't actually matter what it is because we're just trying to find the ratio. And the question is, what's V2? Well, now we just pull in our equation of continuity. So the equation of continuity says that area 1 times velocity 1 has to be equal to area 2 times velocity 2, because the volume of water going in, or fluid, has to be the same as the volume of fluid going out. We now know the ratio of the areas. So what we can do is we can bring A2 over here, or we can bring A1 over here. It doesn't matter which way around we do it. What I'm going to do is I'm going to bring it over this side so that we have V2 equals, we divide that through, we get A1 over A2 times V1. And the reason I've done that is because now it'll tell me V2 as a fraction or as a ratio of, or a multiple of V1. And that was just more logical for me. If you did it the other way, it would be a back to front relationship compared to the question. So A1, we'll leave it as A1. A2, we're going to instead put a quarter A1, because we just found out that that's how they're related. So if we've got a quarter A1 on the bottom and A1 on the top, the A1s cancel, and we're left with 1 over a quarter. And if you need to, you can put that into a calculator, or if you're good at rearranging fractions, you'll realize you can just flip that up the other way and put it up the top. So it's equal to 4V1. So the velocity in this part of the pipe is 4 times the velocity in the wide part. So the volume has to be the same, and that tells us that if the area is 4 times as big, then the velocity is going to get 4 times as big on the narrower part. Right, back to the slideshow. There we go. Oh, yep. So that, as I said in the slide, same reasoning. I've done all of it in one formula, but the same reasoning there, 4 times as fast as the water in the wide part. So now, as I promised, we're going to figure out Bernoulli's equation, but we're going to try and get there through some reasoning. We're going to try and approach the equation. I could just give it to you and then talk about it, but hopefully, as we did with Archimedes' principle, this will just stick a little bit better. First thing is to just think about the scenario. What we want is an equation that works for any pipe that's got fluid flow, or not even just pipes, just fluid flowing from one point to another point. And we want to think about what's going on with that and try and relate our different pressures and velocities and whatever else we might have. So we already talked about the continuity and having a change in velocity due to a change in the pipe dimensions. But if our fluid is accelerating, right, so it's going from some velocity V1 to a different velocity V2. If V2 is different from V1, so if the pipe has changed at all and the velocities are different, that means it is accelerating. It might be accelerating positive or negative, so accelerating or decelerating, but it is still accelerating. And we know from Newton's second law that that means we must have a force acting on that fluid. Choose a tiny little part of the fluid, whether it's a single molecule or droplet, or just an imaginary little cube of fluid in the middle of that pipe or something. For that to change velocity between this point and this point, between two different parts of the pipe, it must experience a net force. We need a force in order to get an acceleration. And now, since we're dealing with a fluid, we already know that forces are easier to consider when we think about pressure instead. That sentence didn't quite make sense, but you know what I mean. We've got a pressure in a fluid is a little bit easier than a force. So if we think instead about pressure, that means that the pressure on one side of our little imaginary cube of fluid is going to be higher than the pressure on the other side, so that we have a net force. And for it to accelerate towards the faster velocity part must be a lower pressure. Right? So the faster velocity must have a lower pressure than the higher velocity. So that's the idea that we've got here. So just by thinking about what happens, we saw with the volume continuity that we have to have an acceleration, and therefore we must have this pressure gradient, a change in pressure. So the wider, slower part must be higher pressure than the narrow, faster part. And so that's just repeating what I just said. We must have a pressure difference on each side of our little chosen fluid element, whatever we choose, whether we think about a molecule or a little imaginary box of it. And it must go from the wide section towards the narrow section. And this is summed up in Bernoulli's principle. Daniel Bernoulli was the one who sort of deduced this and wrote it as a statement, and he said that a change in pressure must result in a change in speed. Other way around. A change in speed must result in a change in pressure if everything else is all the same, if everything else is held constant. One of the most well-known applications of this is in flight, in the shape of aeroplane wings. And as per my little diagram there, you've got airflow being pushed up over the wing at the top, and it has to travel further, it travels faster. It travels faster over the top of the wing than the air going underneath does. Therefore, the faster air on top, this air at the top of the wing, has a lower pressure. And if we've got a lower pressure on the top, higher pressure on the bottom, then we have a net force upwards because we've got similar area on the top and bottom. So different pressures will result in different forces. Do note that this is not the only force helping keep airplanes up in the air. That is not the only thing. It is a well-known application of it, and it is certainly valid. It does work, but there is more going on with airplanes. Noticeably, the wings are often tilted further downwards so that you're actually deflecting airflow. And if you're changing the momentum of the air from that way to that way, then that means you're applying a net force to it. And then by Newton's third law, the air is applying a force to the wing. So you get this actual direct push off as well as the changing airflow. So there's multiple things going on. But regardless, this is still a true statement, but it's not the only thing keeping airplanes up, which is a common misconception. A very simple experiment that you can do is to hold a narrow strip of paper just below your bottom lip and blow across the top of the paper. I might actually give this a try now. I haven't practiced this, so I don't know how well it'll work, but let's try it. Just forgive me while I rip off a little bit of paper. It's not working very well. I'll try that again. So you can try this at home too. While I'm getting my bit of paper, you can get your bit of paper. And so you just want a little strip of paper, and then you're going to hold it to your bottom lip. I'll stop sharing. So you want to hold the paper right here, just below your lip, and then you want to blow outwards. And the idea is that the speed of the air above the paper will be greater than that below it, because below it it's not getting blown. And that means that you've got a lower pressure here, and therefore a lower force downwards than you do upwards. The force upwards will be greater, and so hopefully the paper will rise upwards. All right, so that's not working too well. But you can hopefully see that the idea is there. I should have practiced that and figured out a bit of paper that would work better. But you can have a go at home. Do play with that. Look up YouTube videos. There's plenty of options out there for viewing that. But you can see that concept being applied. Right, back to our slideshow after that abysmal attempt at a demonstration. So do have a go at that. Or as I said, look up a YouTube video or something. If you find a good one, feel free to shove it in the forums. Right. So the next thing we're going to think about is changing height. So we just talked about changing the dimensions, right? Now we're going to say what happens if we change our height. So we've got a pipe, and it's flowing along, and then suddenly it drops down by a meter or some drop. Right? What's that going to do to our fluid? Right? Is the pressure going to change there? We already know the pressure changes in a static fluid, right, when we get that drop, and the same relationship holds for a moving fluid. Right, so the change in pressure will still be given by rho g delta h, where delta h is our change in height. Of course, keeping in mind that if you go upwards, then your pressure is going to decrease. If you go downwards, it will increase. But the equation still stays. The equation still holds exactly the same. And so then we can bring it all together. We've got these different concepts. We've got the pressure itself in the fluid. We've got the velocity of the fluid, and we've got the height of the fluid, so how far up and down the pipe is moved. The change in height to pressure is easy enough. We already said that one. Pressure is already a pressure, so we can equate those terms quite happily. But what we've got is a term about velocity that we've said must result in a change in pressure, but we can't relate our velocity to pressure directly. We need an equation to do that. We can't just take our pressure and say, oh, velocity's changed, and say the pressure must have changed. We need to know how much the pressure will have changed by. So we need that equation to bring it together. And the easiest way to do that is to realize that pressure is actually an energy density, or energy per unit volume. So this isn't something we've really talked about before. We've only ever dealt with mass density, but energy density, or pressure being energy per unit volume, is a very easy way to arrive at Bernoulli's equation. So think about the potential energy given by a height h. We know that that is just mgh. Right? Hopefully we all remember that potential energy is mgh. And we've already seen that density, change in pressure is given by density times gravity times height. So we've got mgh for potential energy and rho gh for pressure. So they're very similar, right? The only thing we need to do is divide our mass by volume. So if we take our potential energy, mgh, and divide it by volume, we get our pressure. So that means we've got an energy divided by a volume to get our pressure out. So we can do the exact same thing with our velocity. We can take our kinetic energy, which is the energy that's that's tied up in that velocity, in that motion of the particles, and convert that into a pressure in the same way, into an energy density. So we get a half mv squared, we divide it by our volume, and the mass becomes a density. We get a half times density times velocity squared. So that is how much the pressure changes as we go from our wide, slow part of the pipe to our narrow, fast part. That change in velocity will give us the change in pressure through this relationship. So now we actually have what we need for Bernoulli's equation. So what we see is that at any 2 points on the pipe, the energy density of our fluid must be the same. So we've got the actual pressure itself of the fluid, plus this energy in the velocity, plus the energy in the potential, the height difference, is equal to all of those terms at the second point. The other way that we often write it is that the pressure plus the velocity term plus the height term is equal to a constant. So no matter where you go in that pipe system, if it's one connected fluid pipe system, then wherever you go, this equation will be true. This constant, once you find it for one location in your pipe, it will be true at every other location in that pipe. And as I've already said, we're talking about energy densities when we talk about pressure. We just don't use that term a lot. So that means that Bernoulli's equation is actually just energy conservation. Right? We have energy in our fluid system and it has to be conserved. So that means that if we lose one kind of energy, so if the velocity drops, then we must gain a different kind of energy. We must either gain some height, some potential energy density, or we must gain some actual pressure energy density. So that's the idea behind Bernoulli's equation. I think I will leave it there and we'll come back and we'll look at applying this. We'll look at an example and then we'll talk about some phenomena in the world that we can see where it is a relevant scenario. So that's the end for video 1, and you'll see me again shortly for video 2.